Test, test. I hope I think it should also work on the recording. Okay, good afternoon. Welcome to this lecture in Advanced Deep Learning for Physics. I'm Felix Köhler, I'm a PhD student with Professor Thury, and today I want to talk about automatic differentiation and adjoint methods. I think over the course of the lecture and the exercises, you've already been introduced to some of these aspects. For instance, during two of the exercises that you had to do where you had to implement manual Autodiff or also as a simple Python program. And this lecture is intended to put this knowledge into a bit more of a general perspective, maybe also frame it from a different point of view, and in general extend on some concepts and make some relations to related fields of science. So you are lucky, this audience is not too big today, so feel free to interrupt me at any point and ask a question. And yeah, let's get started. I want to start with a motivation on automatic differentiation. And for this, I want to look at the very simple machine learning model on linear regression. And if you write down the computational graph for linear regression, you can have something like this, what is here on the slide, where you have an input to your model denoted as x. You have parameters of the model in terms of a weight matrix W, and the compute flow is that you make a matrix multiplication between these two quantities. This gives you a prediction denoted as y hat, and then together with a reference, you compute a loss, and this scalar value gives you like an assessment of how good your fit is. And this machine learning task, or what is the task of linear regression, is to find the parameters W that minimize your loss. And if you take in a machine learning course, you know that there's an analytical solution to linear regression. But if you wanted to do the solution in a deep learning fashion, you might use a gradient descent algorithm. So you are interested in the derivative of the loss with respect to your parameters W. And a way to do that is if you apply what you learned in a backpropagation lecture from a deep learning course, and in that it works as follows. So you first execute your compute graph in this PLEG fashion and save some intermediary variables. And then you execute a second pass through your compute graph, which goes in the reverse order. And for this, you start at the end, at the loss, and introduce additional variables, gradients or derivatives. And here I want to follow a notation that's very common in automatic differentiation, in that you denote derivatives, or we will also call them cotangents, with a bar on top. But for the sake of simplicity, you can think whenever there is a variable with a bar on top, this can be read as if we take the derivative of the loss with respect to that quantity. So what do? Well, you start at your end of your compute graph, you start at L bar, and the derivative of the loss with respect to itself is 1. So this is the starting point of your reverse pass, and then you basically reversely propagate the derivative on information over your compute graph. And for this, I think maybe I can, yeah. So yeah, that's probably better. Okay, great. So you reversely propagate the information over your compute graph, and you go to another gradient on the prediction of the output, and then ultimately you can reversely propagate or backpropagate the gradient into the parameter space. You get your W bar, and this is essentially the derivative you will then plug into your gradient-based optimizer. What is so special about this, or why did I write that down, is to also highlight that the reverse part here denoted in the red computation takes information from the black execution of your model. And this is visible in that we, for instance, in order to reversely propagate the tangent information, you take information in terms of your prediction as well as the reference in order to go to the y hat bar. And also in order to get to the W bar, you need information on your inputs x. And of course, this is a very simple model, the linear regression, but if you write it down in that way, it can already be quite, well, let's say, insightful. But of course, in deep learning, we are interested in way more complicated models. So out of curiosity, I created a similar approach for a multi-layer perceptron. I don't think it's relevant to truly see what is going on here, just to get the glimpse that, of course, it can be complicated. And automatic differentiation, or if you use your favorite deep learning framework, is a tool to take away all this burden and automatically compute all this red based on what you give in the PLEG compute graph. And that's very handy because it allows us in deep learning to focus on things that are more relevant, like for instance to investigate new architectures or other learning methodologies. So let me summarize this in a motivation. So here on the right I have a compute graph which will follow us through the lecture, which is a combination of both a neural network and a physics. So here we abstracted the neural network into one compute blob denoted as NN, which is parameterized by theta. And I summarized this in that form because based on Autodiff and your deep learning experience, you know usually when you use standard architectures, differentiating them is rather straightforward. Here we are interested in a combination with physics, and physics is of course a bit more of a general term here. In that sense, this means a numerical simulator. And the core essence is that if we then backpropagate, and here in that sense we first make a neural network step, make a physics step, compute a loss against the reference, and if we then backpropagate, we also need to backpropagate over the physics, and this is this so-called differentiable physics you already exposed to during some of the other lectures and the exercises. Okay, let's summarize that. Well, the quite obvious statement, neural networks are often big and nested compute graphs with many free parameters. Probably in your experience, you might have trained networks in the order from 10,000 to 1,000,000 parameters, and probably you are aware that most state-of-the-art natural language processing models are in the realm of 100 billion parameters. But still, in concept at least, they are fit or tuned using first-order optimizers, and these first-order optimizers need gradients, and automatic differentiation is the tool that we use to get these gradients. And this is what I mentioned. So if we have physics in the sense of a numerical simulator and it's part of the gradient flow, then we need to differentiate it. And this is what we're going to discuss in this lecture. Let me give you a quick outline what I want to show you here. So the first part of the lecture is going to be to introduce you to a more general perspective on automatic differentiation that hopefully goes beyond what you learned in a backpropagation course. And this is based on a functional viewpoint on Autodiff. This is a viewpoint that I personally like a lot, and it's also something that is emphasized in the JAX machine learning framework. So I will also accompany the lecture with some code snippets from that, but don't worry if you don't understand or haven't looked at that yet. I think they should be self-explanatory. For this, we will start at something that I will call scalar mode automatic differentiation. This will naturally lead us to vector mode, which is doing automatic differentiation at the level of the BLAS operations. I will talk about that in a second. This also naturally leads us to discussing hierarchies in automatic differentiation, and ultimately we will end up at the second part of this, or the second part in the title of this lecture, which is on adjoints, and typically this is referred to what you find in deriving or performing Autodiff on the level of partial differential equation, sometimes also referred to as continuous sensitivities. And all this might eventually require a little bit of a discussion of the history of automatic differentiation and highlights also why we have these different viewpoints. This should be around 60 to 70% of the lecture. Then afterwards, I want to talk about some specialities in differentiable physics with respect to linear system solving and nonlinear system solving. And if time permits, we will discuss some advanced topics. And yeah, okay. With this outline out of the way, let's start with the first part of the lecture, this general perspective on automatic differentiation. So for this, I want to talk about scalar mode automatic differentiation. Likely, if you had your course on backpropagation, you might be exposed to an example like this, where you express a computation from an input variable denoted here as x to an output variable denoted as y in terms of nested computation. So here, for instance, I have the input x, I will square it, apply the exponential, apply the sign, and this will give us the y. And you can say, well, this is a nested computation, let's call it f, but in its core, it consists of three functions, L, M, and N, given by sine, exponential, and squaring respectively. And we can write down this compute graph in, well, in one form, for instance, in that we introduce temporary variables, for instance, to say, well, z0 shall be our input x, then z1 is applying the square to z0, z2 is applying the exponential to z1, and so on and so forth, and then we ultimately end up at our output. Okay, so this is the compute graph for this scalar operation that we want to look into. And automatic differentiation, or the core ideas of automatic differentiation, now arise based on the fact that, well, we are interested in derivatives. So if you take the derivative of the output with respect to the input, you can apply the chain rule of calculus. And here you find, well, we have these nested computations, so we find that we take all the derivatives. So y with respect to z0, z3, z3 with respect to z2, and so on and so forth. And here in that sense, I want you to read this as if we have the concrete value of this derivative. So let's say I give you a value of x, for instance 0.3, and then you execute your compute graph, you give me the output y, and then based on that, you can also obtain the value of all these derivative quantities. And then essentially, well, the chain rule says that we can get the derivative of the entire function by just multiplying the individual derivatives. And this gives rise to two ways to doing automatic differentiation. The most intuitive, I would say, is based on forward mode. So the idea here is that whenever you have multiplication in at least in infinite precision is associative, so you can use any kind of bracketing. And one possible way of bracketing is to execute or to multiply the derivatives in the same order as you also execute your original compute graph. And so in that sense, this means you first multiply, well, the last two derivative values. Once you have the result, you multiply it with the next, and so on and so forth. The advantage of this approach is that it can be done alongside the actual execution of the compute graph, because you have access to the derivative quantities at the same time when you also do the original execution. And here I want to make a remark on the naming that I think is more appropriate here, because I think probably if you're introduced to a backpropagation, you hear the name forward and reverse pass. But I think it's a bit confusing here, because when we do forward mode automatic differentiation, we have kind of another pass over our compute graph, which you might also call it the forward pass. And so in order to distinguish the two, I want to call it the original execution. So essentially what we have here, if I just give you an x and you give me the y, I want to call this the primal execution. And the corresponding execution for forward mode, you could call the forward pass, sometimes also called the tangent linear pass, but there's a lot of names out there. But just to make that clear here. Another way of bracketing these multiplication is called the reverse mode, where we bracket in an order going from left to right. So you first multiply the left two derivatives and then multiply with the next, and so on and so forth. This reverse mode is special in a sense because we cannot compute it alongside the primal execution. Because in order to have the derivative values we first want to multiply, we need an execution of the primal pass, because the derivative of z3 with respect to z2 at a concrete value might depend on z2 at that particular value. And this is also what we saw in the example of linear regression. We need some information from the primal pass in order to execute this reverse pass. Okay, this might be a bit more of a general introduction to Autodiff. I want to go one step further into something that might seem unintuitive at first, but helps us to be more general about talking Autodiff at a lot of different interpretations. And that is that we are not interested in the entire derivative. So we're not interested in the derivative of y with respect to x, but rather the multiplication of the derivative with another number. So think about it like this. In scalar mode, this derivative will be another scalar value. And now I say, well, instead of giving me this derivative value, I want you to multiply that with another number. And this additional number is often called a tangent. And here in that sense, the notation for automatic differentiation is that if we take the forward mode automatic differentiation and apply it, multiply it with a tangent from the right, we call this a push-forward or Jacobian vector product. And you can read this like this. So here, instead of taking the derivative, we multiply it with an x dot. So essentially, so I probably should have put another set of brackets here, but instead of now multiplying the two derivatives, we rather multiply the derivative with the given tangent, then we multiply the result of that with the next derivative, and so on and so forth. We still go in the same order of the primal execution, but we start with x dot basically. And here I have a snippet in JAX where I implement the aforementioned function as a lambda function, and then I call this very nice function within JAX, which is this Jacobian vector product, and this requires me to hand over a function for which I want to differentiate. This is f. Then I need to hand over an execution point. So this is basically the primal point at which we evaluate. So here this is 0.3. And I need to hand over the tangent, which is here I chose 1.0. I will explain in a second. And this basically gives back two scalar numbers. So it will first give the result of the computation, so what the compute graph gives if I input 0.3, and then it will give the propagated tangent. So this is basically, you could also call it a y dot, you might say, so the tangent on the output. Mathematically, I like to think about it like this. Well, this is another kind of a high-level function where we plug in a function f, we plug in this primal point, we plug in this tangent point, and then we get a primal output, and we get this nice tangent output. And there is this very core insight in automatic differentiation in that the operation, so this is something you can mathematically prove if you restrict yourself to some nicely behaved operations. You can say that the number of operations, so for instance think in terms of floating point operations, for executing the entire push forward is less than 2.5 times the operations it takes for the primal execution. And keep in mind, when you do this push forward, you get both the primal output and the tangent output. So you get basically both quantities for the cost of 2.5 times of just getting the primal output. And similarly to the push forward, you can go find this primitive rule for reverse mode automatic differentiation, which is also called the VJP, or the vector Jacobian product, or the pullback. And here we multiply a quantity from the left, here denoted as y bar. And that sense, well, we do similar to before. We just first multiply it with the leftmost derivative, then with the next, and so on and so forth. And here, if you wanted to implement that in JAX, this is basically, well, I call this VJP function, hand over the function f. I will hand over this primal point 0.3, and basically this gives me an output. So it would turn out that this output is, of course, the same value as you also get with the push forward primal propagation. And now instead of the reversely propagated cotangent, you get a function, another function that you can execute and hand over this this kind of starting cotangent y bar, you might say, and this then gives you another value here. So this also highlights this two-stage nature of reverse mode automatic differentiation, in that you first execute the primal pass, so you get the output, and then you get a function or something which performs the reverse pass for you, which has saved all the temporary variables it needs, and then gives you the backpropagated cotangent. Mathematically, you could say, well, the pullback of this function f is essentially, well, we take our primal input x, we give it a cotangent on the output y bar, and then basically we get the output y, and we get a cotangent on x. So if you think about it like in how the information is flowing, in a push forward, primal and tangent information are both flowing in the same order as the compute graph, whereas in the reverse propagation, primal is flowing forwardly and cotangents are flowing reversely. And the fundamental result we know from Autodiff, or from mathematics, is that the operations for a pullback are bounded by 4 times the operations for the primal. So it's like propagating both the tangent primal forward and the cotangent backwards costs at max as much as 4 times just propagating the primal. Okay, why did I do that? So we can also see one thing here is, of course, if you multiply a derivative value, so dy by dx, with so which will be a scalar, with another scalar, you know, if I multiply a scalar with 1, this does not alter the value of a scalar. So essentially, if we hand over a cotangent of 1.0, or if we hand over a tangent of 1.0, as we do here, we actually get the derivative value. So it turns out that this is actually this dy by dx at our concrete point. So we kind of find back the quantity we might actually be interested by just using a 1 here. Okay, cool. So what I want you to take away from this, yes? Yeah, that's a good question. So here in scalar mode, of course, it makes very little sense. It will only start making sense when we then look at vector rules. So here this is just to motivate that, but yeah, if you do this, then not really relevant. 2.5. Oh yes, so this is a mathematical analysis. So there is a very famous book, this by Andreas Kriwank. He's probably one of the well-known figures in automatic differentiation, and they derived that in detail. So this requires a bit of an assumption on what kind of operations your compute graph can include, but is amenable to what you typically see in modern applications of Autodiff. So I would probably also have to look that up in detail. Yeah, so there's not a good intuition why this is higher than the push forward, except for, well, maybe it requires some additional operations, loosely speaking. Kriwank, I will have that also linked in the resources at the end, so then you can take a look. Okay, cool. So what I want you to take away, so as said, it's probably not that directly visible in this scalar mode, but the point is that automatic differentiation is a tool for us to take derivatives of small operations and then combine this into the derivative of a big nested operation. So internally what JAX does is it knows how to take all these individual derivatives, or to be more precisely, it knows how to perform the VJP or the JVP for all the individual operations. And then it cleverly combines that into something that we can use for larger compute graphs. So it, for instance, knows that the derivative of sine is cosine, that the derivative of the exponential is the exponential, and so on and so forth. So it is aware of that, and then it uses this to combine, to derive arbitrary compute graphs. So in summary, we could say that, well, Autodiff is the system to, well, can in its primary modes can either be done in a forward sense, then we talk about push forwards or JVPs, or in a reverse sense, then we talk about pullbacks or VJPs, and it is a system to combine that, or to manipulate the compute graph consisting of elementary atomic operations into a VJP rule for the entire compute graph. And the core point in that, and this is most certainly a big part of this lecture, is that at some point we need to find symbolic derivatives for these atomic operations. So here, in the sense of scalar mode, we did this on a scalar level, but this is arguably not the best way to do it, and we will see that in a second. But nevertheless, you can find a library of how to do this for scalar operations. This is what is deeply baked into the Autodiff engine you use, let it be PyTorch, TensorFlow, JAX, so on and so forth. They all have this ingrained at some point, and you can derive that. Some of the rules might look a bit strange at the beginning, but they are rather straightforward to show. So for instance, the propagation for addition is that if you take two inputs x and y and add it to z, then the tangent in the forward mode is just the output tangent is just the summation of the tangents, and in the backpropagation, the cotangent on the output just reversely flows equally to both inputs. It's a bit more complicated for multiplication and maybe some other operations, but it's usually easy to show. Okay, so now also relating to your question is, well, scalar mode is easy, and it's not relevant for deep learning, maybe only conceptually. So you could now say, well, what we're actually interested in are, for instance, linear regression, are deep compute graphs like transformers or so on, or differentiable physics. How do we differentiate them? And one way to do this would be, well, to remind eventually whatever kind of high-level operations you do, a matrix multiplication, a matrix vector product, and so on and so forth, at some point they will just consist of scalar operations. So you, for instance, probably at some point you might have implemented a matrix multiplication as a triple for loop, and then at some point there are scalar floating operations within that. And so you can just say, well, I define my compute graph, for instance, if I wanted to do a matrix multiplication in terms of this for loop. So you could say that the extension to vector automatic differentiation, so working on tensors, working on arrays, is rather straightforward, because you can write each of the high-level operations in terms of scalar operations, if you just unroll the loops, unroll the conditionals, and so on and so forth. So let's take a look at that, how JAX does that. So here I have an example of a function which maps from a three-dimensional input to a two-dimensional output. So it here takes x0, x1, and x2, and then it maps to 2 dimensions. So this semicolon should separate the two entries in the vectors in the vector. So you could also say, well, x is 3-dimensional, y is 2-dimensional, and you could then say, well, our derivative information will then be in terms of the Jacobian. So the Jacobian is the collection of all partial derivatives for the outputs with respect to the inputs. So we have 2 by 3 if we use the numerator layout. Okay. Implementing that in JAX kind of works like this. So we again say, now we want to do the push forward. So I implement a function which does exactly what I had in the previous slide. I choose a primal evaluation point, so this is just some random numbers. And then I use a tangent point, an x dot, and here I choose 1, 0, 0. I will come to the specific choice in a second. And then again, similar to the scalar mode, I plug in f, I plug in primal, I plug in tangent, I get my output primal. So this is basically the value of the compute graph at the specific input. And I get my output tangent, which is basically the y dot, so my propagated tangent. Similarly, we can do something like this for the reverse mode. So for the pullback operation, so here I defined a cotangent, so it's like this input, this cotangent on the output, so it's a y bar, and here I chose 1, 0. And similarly, we again get the output, we get a function which does the reverse path for us, we plug in the cotangent, and we get the backpropagated cotangent. Okay, so far so good. This is basically now internally using scalar mode. So JAX is using a scalar mode, so far we don't have much about vector mode, but at least conceptually you probably can understand, well, I could also do this for a for loop. Okay, before I come to the next point, I want to make a quick detour of multiplying matrices with unit vectors. So let's assume you have a 2 by 3 dimensional matrix, as you have it here, filled with just some random entries. And if you multiply this with a vector, so you match the shapes, so 2 by 3 needs to be multiplied with a 3-dimensional vector, then I choose a specific vector here, so the first unit vector with 1, 0, 0, and this essentially extracts this column out of the matrix. And if I chose a different unit vector, like 0, 1, 0, it would give me the next column. And I would also get the last column if I chose 0, 0, 1. If I use a row vector to multiply the matrix from the left, so here I just use a column vector and transpose it, and I use a 1, 0, this extracts this 0th row, so it gives me 1, 2, 3. So if I chose 0, 1, I would get 4, 5, 6. Okay, why am I doing this? Because essentially what we now have with our push forwards or JVPs or pullbacks or VJPs are ways to multiply our Jacobian matrix with vectors either from the right or from the left. So we don't have access to the matrix yet. So this is not visible to us. This was just given to you conceptually. But we have a function which performs the matrix vector product. And we can inspect or we can query this function by multiplying it with unit vectors. So it's kind of like using an oracle to give us entries of the Jacobian. So, well, we can make usage of that and generalize that. So we can say, well, now for the sake of generality, I want to say, well, we now have a function that maps from an n-dimensional to an m-dimensional space. So before we had 2 to 3, but now let it be arbitrarily large vector spaces. Then we know if we apply the push forward on this function with a specific input and the ith unit vector, we get the ith column of the Jacobian. So if we say I do it with the 20th unit vector, I can extract the 20th column of my Jacobian. For the reverse mode, we can say we can give the ith unit vector, and then we get the ith row of the Jacobian. So forward mode is the tool to extract columns of Jacobian, and reverse mode is a tool to extract rows of Jacobians. And as such, we can say we can build the entire Jacobian, where we just do a lot of push forwards. So we either do n push forward operations, because we can get each column to then stack them together and build a Jacobian matrix. 1 second. Or we can use m pullback evaluations to build the Jacobian by the rows. And now the crucial insight comes into play, that if we have a Jacobian, or if we have a compute graph where we have many inputs and only if, sorry, I'm other way around. If we have many inputs and only a few, sorry, other way around again, a few inputs and many outputs, so m is larger than n, then forward mode is more efficient because we have a lot of rows but only a couple of columns. You might say this is like a tiny, skinny Jacobian matrix, and then forward mode is more efficient because you might only need to do 5 push forwards. If it is the other way around, so if we have more columns than we have rows, way more columns than we have rows, then reverse mode is more efficient. And now this is the crucial insight. If we have a neural network, you essentially end up having a compute graph that maps from a lot of parameters to a scalar valued loss. And this is basically a mapping from a super high M, which is maybe 1,000,000, or in the case of, let's say, natural language modeling transformers, it might be in the range of hundreds of billions, to a one scalar loss, then reverse mode is extremely efficient. And this is also what you typically see, that the reverse mode is quoted as being constant or scales constant in a number of parameters. And that's very nice. If it turns out that your Jacobian is approximately squared, then forward mode is more efficient, because we saw that doing one push forward is cheaper than doing one pullback. And so if you do as many pullbacks as you do push forwards, then push forwards are the better way to go. Yes, so this is additional overhead. Yes, exactly. So you not only have this theoretical bound, which might not hold in practice, so it holds in practice as being the upper bound, but it might not be the best guidance for what you actually need in operations in practice. So it might be that in practice the operations are almost the same, but yeah, then you're right. The additional overhead for reverse mode comes in the taping or other modifications. Okay, cool. So far we, again, even though we looked at the vector example, we had this idea that we essentially want to do vector automatic differentiation, because this is part of deep learning. But we also saw that Autodiff is this system to combine the primitive rules for elementary operations, and this kind of gives us rise to the question, like, what ends up being an elementary operation? And this is essentially probably what you are using day to day, is automatic differentiation on a level of BLAS operations. So BLAS is this collection of linear algebra operations, so matrix multiplication, vector multiplication, dot products, you name it, and they are at the very core of all machine learning or scientific computing frameworks. So if you use your TensorFlow, if you use your NumPy, it will eventually map to primitives coming from that can be expressed in BLAS most of the time. And then there are highly efficient backend engines like on CPUs or GPUs that execute these operations. So it would be very advantageous to do Autodiff on that level. And here is an example. I have this matrix vector multiplication I already talked about, in that we say this is a function that takes in an input x, a matrix A, and a vector B, and then it computes AX plus B. And we already said, okay, we could theoretically unroll the double for loop, do scalar mode AD, which is probably very inefficient, because in reverse mode we need to do a lot of taping. But we could also define a rule on this very high level. And this is what all these Autodiff frameworks do. So they say the push forward for this matrix vector multiplication is given that, well, push forward always computes the primal, so this is rather just a matrix vector product, but then it propagates the tangent in that way by saying ax dot plus a dot x plus b dot. And similarly, we can also derive a reverse rule for matrix vector multiplication, which is given in that sense. We, for instance, backpropagate the cotangent on the output to the cotangent on x by multiplying the matrix transpose with y bar. They are, of course, a bit more difficult to derive in that sense, but you can do this. And again, they are baked in all the deep learning frameworks. So that's what I want to mention here. What is also very nice is that these systems express their primitive rules again in terms of atomic operations, because you see that in order to do the push forward for matrix vector multiplication, you again do matrix vector multiplication. And this is very handy, because if they then do Autodiff, they can rely again on the BLAS engines they already have available. So the cred function within JAX is always doing reverse mode. So cred is usually just a sugar coating around the VJP. They choose that. I think this is mostly in order to comply with some other frameworks. Yeah. Oh, good question. Maybe I was not precise about that. So it depends a bit on how you implement that. So if you use tensor level of your framework as is, if you say, well, I have my array, matrix multiply with another array, then and you do Autodiff over that, then your engine will do Autodiff at this BLAS level. So this is just if you wrote a Python function which indexed all your arrays and then performed the algorithm for you, like matrix multiplication, then JAX would unroll all that and do the scalar operations. So if you write good code, yes, you probably do, then it will already result to the more efficient Autodiff mode. And you can derive Autodiff on this level. So this is, of course, a bit more complicated, and you, of course, rely that these library developers did a good job on that. And this is what is baked in there. On my website, I have a collection of these Autodiff rules in case you're interested. It's, of course, not relevant of using Autodiff, but it is very nice in deeply understanding Autodiff in deriving these rules. Okay, so far we now had the scalar mode and this vector mode or this BLAS level. So you could either say I do Autodiff on the very lowest level, so scalar operations, which eventually will happen on the GPU and CPU, but might not be the best way to do Autodiff. So I raise my abstraction level and go to these vector levels. And this naturally leads us into looking at hierarchies in Autodiff. I have this schematic I took from a PhD thesis from someone. You can also find it here. And I think he made a very nice point about these hierarchies. So he says that at the very top of what is happening is a mathematical function that you want to differentiate. So let's say it's the matrix vector product. And this does not necessarily tell you how it is actually executed on your computer. This is done by an algorithm, and this algorithm can be given in a sequence of very basic instructions. This can be floating point operations, or a sequence of more high-level instructions like the vector mode we saw. And so essentially what the Autodiff engine does is that it either does symbolic differentiation at the very elementary level, as we saw is a valid way but might not be the most efficient, or it can do it at an intermediate level here. So he says that the hierarchy level goes from low to high. Then he says that flexibility, automaticality, and feasibility goes from high to low. And the performance, of course, is, well, if you do vector mode, is way better. But what we are now interested in is, remind yourself, we have these compute graphs which not only contain neural networks, but which also contain numerical solvers. So you could say the following. For us, we have these three big levels. So we could say, well, eventually, if you do PDE simulation, you do some matrix vector operations. And in these matrix vector operations are scalar operations. So at which point should I differentiate? You could even go, and we will talk about that in a second, that you can do Autodiff on the continuous PDE level. And I really like this perspective on that, because it shows that, first of all, there are multiple ways to do it. And there's likely not the best way to do it, but I will still try to give you some guidelines later. But yeah, so let's maybe continue on with the next slide. So yeah, I already mentioned that. So let me remind you a bit of this compute graph with differentiable physics. So let's say, for instance, again, we have this stuff where we have the neural network first making a prediction and then have the physics afterwards. And here I highlighted the idea of what they're doing by just plotting whatever the result looks like they're operating on. So think, for instance, about a one-dimensional simulation, and this could be your state you're in, looks like this, and then the network does something, it looks like that, and then the physics does something, and it looks like this. So whatever the network does, well, we might not be that interested, but the physics here, if you maybe have a good eye for that, could be interpreted as advection, because it moves the state to the right. So here, in that sense, the peaks are moved to the right. So now we want to do the following. So again, recall we have this compute graph, neural network, does the physics, and then imagine now we have a reference state. So we might say, well, instead of having the peak up here, we want to have another peak being here, maybe. So we penalize if our output here as U2 is wrong or is different from that, and compute this scalar loss. And then again, we do gradient-based optimization, so we have to differentiate through the physics. Okay, again, we say, well, we can differentiate through networks. That's what the Autodiff engine does for you. How do we differentiate through physics? And let's use this idea of the hierarchies in PDEs or the hierarchies in Autodiff and apply it to the idea of differentiating through PDEs. And this might be a way to think about that. So let's say, again, we have this highest level. Let's see it is enwrapped in this most bright ellipsoid. And this is just, well, given we are at state U1, we go to state U2. And the highest level interpretation of that is, well, solve an advection problem for us. So it could be a very black boxy thing. You just give in a representation of your state at U1 and you get out a representation of state at U2 and you don't know what happened. If that is the case and you apply Autodiff to this, then the Autodiff engine might need to be informed how to backpropagate your cotangent or propagate your tangent information over that. And so you might have to do automatic differentiation on the highest level, on this PDE level. But you also know that at some point we have to solve PDEs on a computer. So we could, for instance, implement a first-order upwind method for the advection equation. And these finite difference schemes can be expressed in terms of matrices. So essentially what happens is, in order to advance the state from one time level to the next, is a matrix vector multiplication. But then, wait a minute, well, matrix vector multiplication is on this BLAS-level. So we can also unwrap that and find there the double for loop that does the matrix multiplication. So we have these three levels, but at which level should we do Autodiff? Yeah, that's of course the big question we will discuss in a second. Let me finish for the first half of the lecture by telling you how the rule for differentiating over the advection equation looks like, because so far we know, well, if we have scalar operations, it's super straightforward. It might be super inefficient, but it can be done. If we have vector operations, okay, it can be harder to derive the rules, but we just use JAX, we just use TensorFlow and it works. How does it work on this continuous level? And so here it turns out that you have this primal physics, and I already mentioned you can interpret this as being an advection problem, advancing the state from one time level to the next. So here I said, well, I have this physics over, let's call it calligraphic P, takes in an input. I used theta here, sorry, this is a bit confusing. Imagine that this is the previous state, and it just say, well, integrate from t0 to t equals delta t. The following equation, for simplicity, I chose periodic boundary conditions, and I basically say that the input is the previous state. So if that is the case, you can also derive your reverse rule for the primal physics. And now this second name of the lecture comes in, that this, if you do reverse mode, is also typically called adjoint physics. So the adjoint physics for the advection equation looks like this, in that you say, I have cotangents on the output, I have cotangents on the output given as u bar, and I get my cotangents on the input given as here theta bar, sorry, the name is a bit confusing. And the point is that this advection physics goes reversely in time. So it says integrate from the end, from t equals delta t to t equals 0. And the equation also looks different. You see that the equation has a sign flip. So in case you're familiar with the advection equation, the coefficient in front of the spatial derivative gives you the advection speed. So for instance, if there was a 2, then our solution would be moving twice as fast. If we use a negative sign, it's going in the opposite direction. So this is just to give you a little bit of a taste of what these adjoint physics look like. My experience is that they, especially for realistic PDEs like the Navier-Stokes equation, are quite hard to derive. And here I also very simplistically chose periodic boundary conditions because they also make it easier. But again, you can find this library of functions, if you will, and then you can do Autodiff at this very highest level. Okay, so this should be a good point to make a break for 5 minutes, and then we will continue with the second part of the lecture. Okay, let's continue with the second part of the lecture. So we looked at scalar mode, we looked at vector mode, we looked at this PDE level mode, you might say continuous adjoint. So for now, probably most of the rest of the lecture will be mostly focusing on reverse mode, because that's usually what we are mostly interested in when we do deep learning and differentiable physics. So this could lead to some buzzwords, and this is typically what you see if you have a more perspective coming from optimal control. And there typically people talk about discretize then optimize versus optimize then discretize. And think about it like this in the sense of, do we first derive the continuous adjoint and then discretize it, or do we discretize first and go to the vector operations and then use our Autodiff engine from JAX to differentiate over that. That's a way to think about that, but I think this kind of neglects a bit that it's actually more of a spectrum. So far I only presented 3 different hierarchies levels, but I'm pretty sure you can imagine there might be some nuances in between those. And I think that this DTO and OTD sometimes neglects this approach a bit. But nevertheless, I want to use it as a way to kind of say, well, for the OTD approach, we actually say we are on a higher level versus the DTO, we are on a lower level. So let's compare these levels. So here, so far, we looked at 3 major levels. So we have the PDE level, we have the BLAS level, and we have the Scalar level. So on which level do we do our VJPs, or at which level our Autodiff engine needs to be made aware of VJPs? And for PDE, I would call it a functional level, but it's a bit hard to truly say how to call that. But it's essentially we need to derive these continuous adjoint PDEs. For the BLAS level, it is at tensors, so as we find them nicely in our major deep learning frameworks, or for Scalar, obviously at a scalar. So this is also something we looked at, that when we do reverse mode, it's of course crucial how much do we need to save, or how much do we need to tape during the primal pass to then use during the reverse pass. And here's of course that when we are at a higher level of interpretation, then we might come out with just doing less of those. So for instance, for the PDE, oftentimes it's fine to just save the result. The plus needs to solve every algebra operation, but it can totally connect what is happening within the loops. Or the scalar, it of course sometimes needs to save every float, and that can of course become extremely expensive if you have big compute graphs. So what is the corresponding tool? So for a scalar mode, there are some scalar AD engines. Most of the deep learning frameworks also support scalar mode, because at some point you might do operations that require indexing. And sometimes these Autodiff engines from the deep learning frameworks are so good that they can if you write, let's say, suboptimal code that uses indexing, they then modify it that it uses BLAS operation and becomes more efficient. But of course, if they didn't do any of these optimizations, they could also do scalar AD. The tool for the highest level is oftentimes, unfortunately, manual labor. So this is something that is not often very easily to automate, and there are some attempts to do this. One of the most famous attempts is probably the package called Phoenix or Dolphin Adjoint, which works on a weak formulation of PDEs and has some mathematical guarantees that for certain classes of PDEs it can automatically derive the adjoint rules. But my experience was that of course you need to invest a lot of energy into making it work with Phoenix, so it might not be as easy to do as with the machine learning frameworks. My personal perspective, you don't have to agree on that or take this perspective as well, is that, as said, I don't really like this distinguishing between OTD and DTO. I rather think that we have higher levels of abstraction and lower levels of abstraction. So I would like to say that the BLAS level rules are kind of like the OTD for scalar mode AD, because they don't open the black box of how matrix vector multiplication is implemented, whereas PDE rules are the OTD for tensor mode, because they don't unwrap or open a black box how we solve PDEs. And I think that looking at it from this perspective explains large parts of the history of automatic differentiation. And I have this very nice slide from a presentation, but I unfortunately lost the source of it. And this nicely categorizes the development of Autodiff into 3 distinct periods. So I think Autodiff in general is closely related to development of machine computers. So you don't usually find really very relevant works before the 1950s. Of course, they are built on the chain rule, so you maybe can trace it all the way back to Leibniz or Newton, but I think most relevant aspects of Autodiff only become really crucial once you also have computers. And in the 1960s, he listed, or I think he listed some of the precursors. They did work in continuous automatic differentiation. So they derived the adjoint rules in the context of optimal control, so to optimize some dynamics. A very important contribution was by Vanguard in 1964, who is attributed the invention of the forward mode AD. In the 1970s, usually the Finnish scientist Linnainmaa is associated with the invention of backpropagation or reverse mode, although he did it more in the context of error propagation rather than derivative propagation. There have been some other influential work, but probably most notable for people who did a deep learning course is the paper by Rummelhardt from 1986, which was called Backpropagating Errors, or something like this, and this introduced the name backpropagation. And they, of course, made some relations to existing works, but of course they probably to some extent reinvented what other people already had before, but they made a very important contribution in making gradient-based optimization and this cheap gradients that you can get by reverse mode aware to the machine learning community, and this sparked a lot of research in that field using that. We already had the name, so Andreas Kriwank, he is usually related to the more mathematical perspective on automatic differentiation, proving stuff and so on and so forth. Maybe not too relevant for practically using it, but still a very important field or very important subfield there. Okay. So let's close this first part of the lecture with a comparison between OTD and DTO. But I would like to more think about like doing Autodiff on the left column being on the higher level of abstraction versus doing Autodiff on the lower level of abstraction. So let's first do the comparison in terms of derivation. So this means how much manual effort is there involved, and in OTD, usually when you do it at a higher level, it is more laborious because, as you also saw, the rules for higher level Autodiff are way more complicated than for lower level. So you lose a lot of the automaticity you get when you do it in lower level. So here the DTO approach wins. Intrusiveness means when you write code, how will the Autodiff engine use that code? And of course, if you do OTD and you say, well, I want to differentiate over PDEs, I want to do differentiable physics, then you could say, well, I don't want my Autodiff engine to go into my advection solver or my Navier-Stokes solver. This could also be because you write this in a different language, like Fortran, so it might not be differentiable at all. And so the OTD approach here can be beneficial because you never have to open the black box, whereas the DTO requires code to be written in a differentiable way. And this can, of course, sometimes be a bit more complicated. Usually in the performance, OTD tends to be faster, but of course requires you to also implement it in a correct way. The DTO can be slower, although this greatly depends on the problem you're solving. When I think about that, this always loosely reminds me of a comparison. Well, if you do manual code optimization, like writing your own SIMD extensions versus just using the optimizing compiler, maybe this is a loose way to think about that. A second way to compare these two approaches is to first in terms of memory. We already say that the higher level of abstraction you go, the less you have to tape in reverse mode. And this is also usually why people escape to higher levels. And there's a lot of performance tricks you can do to really reduce the memory footprint. Whereas, of course, in the worst case for DTO, you need to tape all intermediary steps, although there are also some techniques to reduce that. And then I have the point of exactness. So of course, Autodiff has the advantage that it usually produces exact derivative information because it exactly derives what is going on. So it does not do any finite differences, which have truncation errors. It does not do symbolic differentiation, which has blowing up compute graphs. So it usually is quite exact, but still there's a difference between OTD and DTO. because if you derive a rule on a higher level, you kind of go away from the operations that truly happen. And you can always see that in the difference between scalar mode and vector mode. Once you go into the vector mode, you lose the scalar operations that happen. Usually within vector mode, it's not that critically visible, but in the OTD-Detour approach in terms of PDE versus vector mode, you clearly see that, because in the reverse mode, you could use a different discretization for the advection equation. So here in the example before, I used the first order upwind method for the primal advection, but you could use, I don't know, a fifth order method for the advection equation, or the other way around. So sometimes there might be some differences between the gradients. I gave that a blue tick because usually that's not a big deal, but oftentimes the DTO has the advantage that with respect to discrete objective, we have the gradients tend to be more exact. Yes, please. So I think you relate to this probably some stuff that investigates related to neural ODEs, I guess. Okay, maybe it is related to that, because a usually trick that you employ when you do adjoint with regards to time is that in order to avoid saving, so when you do an integration over time, you get a trajectory maybe, and in the DTO approach, you would save all steps on a trajectory. And maybe an adjoint approach might allow you to only save the end, and then when you go reversely through the physics, through your adjoint physics, you can then recompute the trajectory by going reversely in time. So when you go, the adjoint physics does both the reverse propagation and the reverse primal solve. And oftentimes this can be problematic if your system is chaotic, which molecular dynamics are. So I guess this could be related to that, but I don't think it might be too related to vanishing and exploding gradients. Sorry, I have to think about that. Yeah. Okay, let's finish this with the question on debugging. So my experience with debugging OTD is that it's extremely hard, because you not only have to validate your primal code, you also have to validate your adjoint code, and this can of course be quite a lot of work. Whereas for the DTO, it's often okay-ish. That depends on the problem. I mean, if you ever looked at the reverse code that's produced by JAX or TensorFlow, it's of course debuggable, but it's not very nice. So of course this can be hard. Let's finish this section with my advice. So I would recommend you, for differentiable physics, to use BLAS-level DTO, but be aware of its shortcomings. So this means there are some catchy things we will talk about in a second, and switch to the fully continuous OTD approach only for hardcore performance optimizations. At least this is in my experience. Your mileage may vary a bit, but I think this is also what we emphasize in this course here. And this is also the reason you find that a lot of physics-based deep learning research uses simple numerical solvers re-implemented in Python, because then they can take advantage of the discrete Autodiff engine, and this is usually very hard if you have like external solvers and need to continuously adjoint derive them, and yeah. Okay. This is the first part of the lecture, so this was 70 to 80% of the content I planned. We probably will not be able, unfortunately, to go over all the topics, but I think that is okay. And I will just quickly introduce one more aspect I think is highly relevant, and then see how much time there is left. Okay, so far we talked about, of course, the intent to differentiate physics, but we assumed that all parts of the differentiable physics pipeline can be easily expressed in terms of the primitives that the Autodiff engine is aware of. And this, of course, allows you to do a lot of things. But as you might have seen, that a lot of the problems in physics simulation boil down to solutions to linear systems of equations or nonlinear systems of equations. And usually applying naive automatic differentiation to them can become a problem. And to give you an example, I have here taken some code snippet from a 5-flow demo. So this is a solution to an incompressible Navier-Stokes equation with a passive tracer, or not a passive, but a species embedded into the flow, which is given by a hot smoke. And this creates an effect due to buoyancy. And if you simulated that, you would get this very beautiful smoke plume. So what does it do? So it first initializes some variables, so it's of course Phi-flow specific. Then it has a step function, which basically iterates over time, and then you get a simulation by repeatedly calling the step function. And after some time, you then get this beautiful pattern. Okay, so this step function does a couple of things. So here, Phi-flow usually uses an operator splitting approach to the Navier-Stokes equation. So it first advects the passive tracer, here called S. Then it computes the buoyancy force. It advects the velocity. So this is basically part of the Navier-Stokes equation. And then it does something very interesting. It makes the fluid incompressible. So what does that mean? So usually when you do an advection step, or if you advect your fluid, it can turn into a state where it is no longer incompressible. And this is, of course, a requirement. If you make an incompressible Navier-Stokes equation and it's not incompressible, then there's something going wrong. And essentially, this is what Phi-flow does here. But the crucial point for us is that at this point, Phi-flow solves a linear system of equations. I can also highlight that here. So we can say that the requirement on continuity for fluid is that the divergence of the velocity field has to be 0. And this can be turned into a Poisson equation, which is in that sense often called the pressure-Poisson equation, in that we find this additional variable, the pressure, which is given as the solution. So here the nabla squared is the Laplace operator applied to the pressure, is basically given as the divergence. And here I use the index star. So this is basically the fluid field after an advection step. So this divergence should be 0, but it is not. So it actually becomes the right-hand side for the Poisson equation. Sorry. And then essentially we can correct the velocity field. This is maybe a subsequent step. But the crucial point is that if we discretized this system, so here again, let's say, again, as said, we use this approach. We are in Python, so we re-implement our solvers. And here we get that this discretizes into a linear system of equations. So a system matrix A with a discrete representation of the pressure, a very long vector, a lot of degrees of freedom, and a very long right-hand side with a lot of degrees of freedom. How do you solve a linear system of equations? Well, there are a lot of algorithms to do so, but for these big problems that Phi-flow solves, the default it recites is to the conjugate gradient algorithm. So I pasted it here. It's not relevant to look at all the details. It's a very elegant algorithm, iterative algorithm to solve linear systems. And it basically does so by involving the matrix and the right-hand side at a lot of steps. We can abstract all this mathematical complexity into a very simple compute graph. And that we say the CG algorithm basically performs a sequence of operations. So it starts at an initial guess. So we again recall we want to find this pressure, and it starts as an initial guess for the pressure field, and then it applies a step for conjugate gradient to get a better guess for the pressure. And it does so over and over. Depends a bit on how the problem is conditioned. Maybe you do 100, maybe you do 5,000, sometimes even more steps of conjugate gradient. And in each step of conjugate gradient, the matrix A and the right-hand side B is involved. And now again, we are in an auto-differentiated setting, so we now want to differentiate over that compute graph. And so what we do is, well, we take all the operations within this compute graph, you would say unroll them, and then differentiate through all of them, and we have to contribute a lot of gradient or cotangent information into either the matrix or the right-hand side, depending a bit on to what we are going backwards into. And this should ring a bell, because we already saw that when we compared scalar mode and vector mode automatic differentiation, we could express vector mode in terms of unrolling the double for loop of matrix vector products. And here we saw, well, we can differentiate through a conjugate gradient method by unrolling all its CG steps. This is one way to do it. Well, let's go through what happens. So first way to differentiate through a CG solve. So we unroll iterations, we build a potentially very long compute graph, and then transform it. So we could also do forward mode, but as said, now we are mostly interested in reverse mode. In terms of Autodiff, this is also called unrolled differentiation. The advantage is that it gives us the exact derivative of all operations. Again, this DTO versus OTD advantage. It is automatic because it does not require any modifications of the code, but as you might have guessed, it is very expensive because we need to tape all iterations. And if you do 10,000 iterations and each of your state is this pressure vector and you have maybe it is 100 or 200 kilobytes, then this already can be quite a large memory on your tape. And the detail, unfortunately, we won't have time to discuss, is that the convergence of the derivative might be different from the primal convergence. This is a very interesting observation. In the first glimpse, it might contradict with being the exact derivative, but I will just leave that here for completion. So what is the alternative? So the alternative is, again, we introduce another level of abstraction into our Autodiff. So instead of unrolling the CG, we say, well, CG solve, it's a black box. So we derive a custom reverse rule, or if we did forward mode, a custom forward rule. But again, let's focus on reverse rule. So we find a custom adjoint rule. And this is also what 5-law does, by the way. So it nicely takes away that burden from you. And this, in terms of Autodiff, is called implicit differentiation. And the advantage is that it can be faster, and it's oftentimes the preferred way to differentiate over linear solvers. It definitely has less memory consumption because we don't need to tape all iterates. Disadvantage requires some manual effort because, well, we need again to derive a custom reverse rule, and it might be hard to get right. So this is a bit of an experience, so that, of course, with linear solves, it can still be okay-ish, but for more complicated stuff, it can become hard. So again, I will show you how this rule looks like, but don't discuss how to derive it. But essentially what happens, you could say that the primal way of executing a linear solver is to say, solve my linear system for x. So I give you A, I give you B, you give me x. And then what would be the reverse rule? The reverse rule turns out that we have cotangents on the output, so x bar, and we solve another linear system in terms of A transpose. So we have A from the primal pass. Again, this also should give you the sense that for doing a reverse pass, you need information from the primal pass. And you solve this for an additional variable, here denoted as lambda. And then it turns out that the cotangent on the right-hand side is exactly this lambda, and the cotangent on the, sorry, this does not work, but the cotangent on the system matrix turns out to be the negative outer product between x as lambda and x, and here again you also need the x from the primal pass. So the adjoint rule is again given in terms of a linear solve, but this time with A transpose. And remind yourself, when we had this vector mode, we also saw that that the reverse propagation is again expressed in terms of these BLAS-level rules. So in order to propagate matrix vector multiplication forwardly, we also do matrix vector multiplication in the tangent propagation. And that's quite neat. So this is also, as said, this is what 5-law implements. So it just does another solve with the matrix in order to backpropagate the cotangent. I have a simple example here how to do this within JAX. This might, of course, be Autodiff engine specific, but just to give you an idea of how that is done. So here, let's say you have a function that implements your conjugate gradient solver. I gave it an underscore here because this is your low-level implementation. You don't want to expose to the Autodiff engine. You create a higher-level function, a CG solve without an underscore, and this basically just calls your CG solver. And then you wrap that into a decorator so that you let JAX know, hey, Autodiff engine, once you encounter this function, I don't want you to open the black box. I will rather give you information how to propagate gradient information over it. And this is in terms of two functions. So you need to define a forward function that is executed in the primal pass, where you solve the linear system. And you save some information on the that is going to be used in the reverse pass. Here, I think JAX calls it residuum information. So you will then unpack that again for the backward function, do another CG solve, but with the transpose matrix, and then return the backpropagated cotangent information. So point is that you see that both in the forward pass you do a CG solve, and in the reverse pass you do a CG solve. Okay. So this is the idea of linear solvers, and I would give you the option. So I think we have 15 minutes left. So we can either go a bit more into detail, a second part on nonlinear system solving, or to discuss some advanced topics. That's up to you what you prefer to look into, or if you want to close early, we can also summarize and wrap up the lecture before that. Yes, then let's go to the advanced topics. So just to briefly skim over the second part, so I also discussed nonlinear system solving. So here, Newton-Raphson method, but the point I wanted to make is that you can also unroll differentiate through nonlinear solvers, but there it turns out that doing adjoints is even better than with linear solves. So bottom line is, for these differentiable physics, better do implicits. Let's skip over that. Yeah. And here I also again link to a table I have on my website where you can basically see a collection of rules for these implicit stuff for a lot of operations you find in differentiable physics. And here I neatly say, well, you can then plug in another layer of abstraction. And this is what I meant. This level of doing Autodiff is very nuanced, and you can find levels in between. And so going DT or OTD might not truly respect everything that is possible. Okay, cool. Let's talk about some advanced topics. So the first topic I chose was is what I would say are continuous representations for neural networks. So far we kind of looked at it in a way that we want to differentiate over PDEs, and PDEs are these multiple layers of hierarchies, going from PDE solving to matrix vector products, or maybe even linear solves to matrix vector products to scalar operations. And oftentimes the best way to differentiate them, or what we believe in physics-based deep learning is the best way to differentiate them, is on the discrete level. And there are some works in deep learning that take neural networks and say, well, they are just discrete operations. Maybe we can find the continuous counterpart to them. And probably the most prominent work in that direction, I already mentioned that, is neural ODEs, where you basically say that your inference of a neural network is given in terms of the integration of an ODE. And they essentially then differentiate that with continuous adjoints. It's also an example taken from their paper. But the point is, like, they go into this continuous objective that they say, well, we want to go away from the DTO and push into the OTD because we think that might be better. So for instance, in the sense of being more parameter efficient, being more efficient to have less memory consumption and so on. In my experience, at least I haven't seen much in this field of research over the last 2 years, so I think probably they're just too complicated for most deep learning researchers to really use, but worth mentioning. Similarly, one can also define deep equilibrium models, and there the inference for the neural network is given in terms of a root finding problem, so where you apply a Newton-Raphson method, and then you do an adjoint linear solve, so they also have this kind of flavor. Then one piece of research I particularly like, I would call it auto-implicit differentiation, because so far a general theme of this lecture was that whenever we go to a higher level of abstraction, it is more laborious to derive the rules for that. And it's very handy if you can come up with tools that maybe take away a lot of the burden and put back the automatic into automatic differentiation. And this is what this paper essentially does. It's by Blondel from 2022, Efficient and Modular Implicit Differentiation. And essentially the core idea is that you define a so-called optimality condition, and then based on this optimality condition, their library registers ways to propagate tangent or cotangent, depending on which direction you go, in JAX. And it does so by internally doing adjoint linear solves with matrix-free operations. It's of course a lot of terminology here, but the point essentially is that they used it in terms of hyperparameter optimization to differentiate over rich regression and so on and so forth. Another interesting piece of research, and then luckily we will make it to that point, so I already mentioned that earlier. Oh yes, please go ahead. Yeah, it's a good question. So here in that sense, let's look at their code example then. So I took this, screenshotted this from their paper. So basically here, as mentioned, they do ridge regression. So ridge regression is linear regression with L2 penalization. And they want to do hyperparameter optimization because you need to set the intensity of penalization. And they want to find the best way to do penalization there. And basically what they define is, so they define this f, which is the optimality condition, and they say this is the gradient of f. So basically this should be a function which takes in both the input as well as the parameter and then maps this to this residuum, basically yes, to the optimality. And here they say you can think of it as the objective function, so you want to do an optimization, so similar to what we also had in the intro with linear regression. And then, of course, the optimality condition, in order to find the minimum of an objective function, is that the derivative has to be 0. And so they use another trick here in JAX. For instance, if you did apply this to linear system solving, you would say that the residuum has to be 0, for instance, and this would be the optimality condition. And then based on that, it derives the rules for you. Does that answer the question? Okay, great, cool. Then another piece of research I find very interesting is the curse of unrolling. So this is related to what I already mentioned with that when you unroll different conjugate gradient methods, then it can actually happen that the derivative convergence is different from the primal convergence. That's a very interesting and super counterintuitive phenomenon. They have a neat example in their paper where they say, so this depends a bit if you are familiar with seeing convergence plots of linear solvers, but essentially what they have here is a semi-log plot, so logarithmic in y and linear in x. And then on this plot, the error for most good converging algorithms should be a straight line. So the slope of the straight line depends a bit on how well you converge, but it should be a straight line. But the point is, on the left, they see how good is the derivative if we unroll differentiate, so don't do implicit diff, but unroll differentiate over this method. Then we actually see that the derivative gets quite bad, so super counterintuitively. So it does not converge linearly, but it rather converges in this super weird format. So in the beginning, it kind of goes up, and then we see that this maybe light green curve, it first goes up, then it goes down, and then eventually it converges linear. That's super counterintuitive. They stated this in their way, they call it the curse of unrolling. They say to ensure the convergence of the Jacobian with gradient descent, so basically the derivative, we must either accept that the algorithm has a burn-in phase, proportional to the condition number, so this is this burn-in phase, or we choose a small step size that will slow down the algorithm's asymptotic convergence, meaning we just have to make CG converge slower. So you don't want your CG to converge slow, so you want to converge it fast, but then you will get burn-in. So there's a lot of open questions that still need to be discussed within Autodiff. So I think this is a paper from 2022. Yes, depends a bit on what you want to achieve. I mean, ultimately, when you do optimization, you want to have exact gradients and not necessarily an exact estimate of your loss. So yeah, it's a good question, and actually this insight leads up to quite a lot of questions. Yeah. No, this is actually theoretical, so they can prove that. Of course, they restrict themselves not to, I think I wrongly said conjugate gradient, so this conjugate gradient algorithm does not fit their assumptions. Yeah, this is actually provable, and you can also observe that empirically. And if you're interested, I can also share you a Jupyter notebook with you. Yeah. Okay, cool. Last topic I want to present is actually research done by Patrick, who did the lecture last week. And so far, because we talked about automatic differentiation as this tool to transform compute graphs, and it does so by just doing all transformations possible. But if you ever used a deep learning framework, you might have encountered this idea to stop gradients, which you, for instance, do to avoid exploding or vanishing gradients. And what you can also do is you can strategically use these gradient cuts to achieve desirable properties. So this is an example you might recall from last week's lecture, where you have a rollout with a simulation state S0, S1, and S2, and then you advance the state through a simulator, you have a neural network acting as a controller and giving you some information into the simulator to advance. And then basically here at S1 and S2, you compute a contribution to a loss. If you do the reverse part over that compute graph, you might get an image like this, where you start again at the end, at the loss, with L bar being 1, and then you have a direct contribution into the parameter space of the network through the first state, you have a direct contribution through the second state, and then there is the so-called backpropagation through time taking place. And since there are two ways to go from a second state to a first state, one is going through the simulator, one is going through the simulator and the controller, there are these two ways gradients propagate reversely. And what Patrick argued is that this is a very undesirable way to go, and we should strategically cut that. And this leads to some advantages in the optimization, so maybe a more desirable optimization for the actual problem within the parameter space. But what I find is a very interesting insight is that so automatic differentiation is this tool to manipulate or to automatically take gradients. And something that I learned from this is that when you take gradients, so the derivative or the gradient field corresponding to a loss landscape is actually rotation free. So meaning that if you have a minimum, then all gradients are pointing towards that minimum. But if you fiddle with the automatic differentiation engine, either by gradient cuts or other kind of issues you have, it could actually be the case that you introduce rotation into your gradient field. So instead of the arrows pointing directly to the minimum, they might create a swirl around the minimum, which can be both advantageous and disadvantageous. So this is also still an open point of research where Autodiff still needs to be discussed. Okay. I have some additional topics here. For the sake of time, I will just, if you're interested, take a look at them at the lecture slides. And I want to also mention here, if this is something that interests you, then please get in touch with us. So there's a lot of interesting things that still need to be researched there. Of course, arguably they are very theoretical, but definitely very interesting to take a look into. So either contact me or Patrick is also interested in that, and let us know. Okay, let's conclude. And concluding with a summary of that lecture. So probably the most important takeaway also from the first part is that automatic differentiation is this system to combine primitive rules for atomic operations, either in the forward sense with push-forwards or JVPs, or in the reverse sense for pullback or VJP into the PJPs and JVPs for larger compute graphs. And in the largest sense, it could be the compute graph we looked at, the parameter space of a network together with differentiable physics into a loss. And this brings up the question that we need to define these atomic operations, and they are usually come with symbolic derivatives, or you might say custom rules in how to propagate derivatives over that. And the important takeaway is that this can be at a lot of levels. There's actually probably a discrete, but still a spectrum. In the lowest level, all the scalar floating point operations, vector operations, or in the sense of the continuous PDE, where you find adjoint physics. And then this is also relating to your question that when you take gradients, so Jack's grad function is essentially just syntactic sugar around that. So conceptually, all Autodiff engines do things like these JVPs and VJPs internally. They might not call it like that, or they might not even be aware of that, but this is the fundament of all Autodiff. And so essentially when you then do, for instance, PyTorch.backward, or if you do Jack's grad, or whatever kind of Autodiff engine you're using, internally it will conceptually do something like what I showed. And then one thing I want to give you as an advice, that for Autodiff it is always important to think input-output. So for the problems that we are considering, that even if you use continuous adjoints or PDE problems, inputs and outputs might still be discrete. So even though we use continuous reverse or forward propagation rules, we are still operating on discrete optimization problems. And so this can often be quite a helpful viewpoint of understanding automatic differentiation. Okay, and then some last maybe happy point to take away is I showed you a lot of details of automatic differentiation, but as you probably are aware that most of the deep learning progress that's happening over the past years is also to a large extent pragmatic. And people just do things. They, of course, could care about all the details, but oftentimes it turns out that it just works, and that's very surprising actually in deep learning. And oftentimes it also works with slightly inaccurate gradients, and to a large extent it's super stochastic. So how does it all come together? Of course, we would like to understand that, but we can only do it for very simple models. So in order to maybe do good deep learning as well, it's also helpful to just get the gradients flowing and not worry too much about Autodiff details, although they can be very interesting. Okay, cool. These are some resources. I also mentioned the book by Kriwang, for instance, some other stuff, or some other cool resources I find. Yeah. Then thank you very much for your attention. And yeah, I'm happy. If you want to have any questions, then please come front. Okay, thank you.